Okay, this is just the memo for our first tutorial test, and I just want to take you through each of the questions just to see that we do these correctly. All right. So the first question was just a basic one on nomenclature. As organic chemists, we've got to know the names of things and how we can work, recognize and talk the language of organic chemistry. The two functional groups over here, we have the carboxylic acid, and then also the nitrile functional group that was sitting on the aromatic ring. How do we describe the relationship between the functional groups on the benzene ring? Well, they are meta-substituted to each other, so the correct answer to this was meta. It's a 1,3 substituted aromatic, and that's called meta. How many pi bonds? A lot of you got this correct. It was a bit of a trick question. There's 1, 2, 3 in the aromatic ring, but there's 2 over here. So 1, 2, 3, 4, 5, and 1 over here, 6. So there are 6 pi bonds in total. That really should have been pretty easy, and you shouldn't struggle too much with that. Question 2 deals with molecular orbital theory. So here, use a molecular argument. Why is the C atom of the nitrile anion the better nucleophile? Well, the reason for that is nitrogen is more electronegative. And then because of that, so its orbitals are at lower energy. Okay, that's the first mark. And so we're comparing this. We've got C double bond N. There's a lone pair of electrons. There's a lone pair of electrons on carbon. So its orbital is at lower energy. So you've got these two lone pairs. This one is at lower energy than this. So therefore, carbon's lone pairs are the better, highest occupied molecular orbitals. All right, so they are better, and they're going to be much more nucleophilic, and that answers that question over there. Straight from class. Okay, next molecular orbital question over here talks about and this was misunderstood by a lot of people, I think. So the addition of nucleophiles to alkyl bromide, C-bromide, the LUMO, pi star of the C-bromine bond, accepts electrons from a HOMO, the nucleophile, that we should understand. However, the LUMO has 2 lows, you can see below, yet one is attacked by a nucleophile. This is one orbital. It's not 2 orbitals over here, it's 1 orbital. There's a node in the middle, and it's empty because it's the antibonding orbital, sigma star. And the nucleophile, we know, comes in from there. The question is, why does it not come in from there? And the simple answer to this is that bromine is more electronegative. All right, in other words, it's delta minus. Therefore, it repels the nucleophile, Nu minus. All right. It's just an electrostatic thing. Nucleophile is negatively charged. It's going to try to come in. It's going to be kicked off by the bromine being more negatively charged. So that was the answer to that. The next one was drawing in the molecular orbitals for the addition of an MEO minus to an aldehyde. Remember, this goes on over and over again, the addition of nucleophiles to carbonyl groups. And so here, this one has 3 lone pairs of electrons, but we can just draw one of the orbitals that's going to interact. I'm going to draw, because this is the angle of attack, so I'm just going to draw this one over here and actually draw 2 electrons in. So this is the highest occupied molecular orbital that we're looking at, and it's going to interact with the pi star of the pi bond, of the carbonyl, should I say. And these need to be shaded in because there are, this is one antibond. The whole thing is pi star. You could have labeled it pi star. I didn't give a mark for that, but mainly it's the LUMO. So drawing it out correctly, get a mark. Drawing that out correctly, get a mark. And then half marks for labeling HOMO and LUMO over there. All right. What is the angle of attack? Most of you got that right. I've said I wasn't really going to ever ask that except for this bonus question. It's 107 degrees. It's the Berge-Dunitz angle. One or two of you actually wrote that as well, which is good. Why is the reaction much slower on this compared to the aldehyde at the top over there? The answer to that is steric hindrance. All right, so steric hindrance, and that is because it's these two carbons over here. I mean that when the nucleophile comes in, there's a little bit more bulk around that, which makes it more difficult for it to add in over there. This should have been a very easy question over here, identifying the hybridization. So we look at the shape. The shape of that is tetrahedral, so it's sp3. The shape of that is trigonal planar, so it's sp2. The shape of that nitrogen, if you work it out, is linear, so it must be sp hybridized. And there's 3 marks for that. Most of you got that correct. Question of acids and bases, I think, was done pretty badly. You've got to know your just general pKa trends over here. Carbon nucleophile, or base, shall I say, carbon C minus type of thing over there. It's the most strongest base that you're going to have, so that is definitely going to be number 1. Nitrogen is always number 2. O minus will be number 3, and this is an O minus, but it's a stabilized one, so it's actually not as basic as that. This is the carboxylate conjugate base of acetic acid, so that must be number 4. Is the following compound aromatic? Pyridine? Yes, definitely. 1 mark. Why? Because it obeys the 4n+2 rule, which is also the Huckel's rule. And I would have given, if you wrote both of those, you would have got a bonus mark for that. You would have got 3 marks instead of 2. And then, all right, so what's happening is with the reactions and mechanisms over here, this is a reduction of the ketone. So we do that quickly, so we draw that out. What's happening is it's the BH bond. So we've got BH4, so sodium boron hydride. There's a negative charge over it, but it's the sigma bond adds to the ketone like that. We're adding an H to the ketone over there. That would have been the lion's share of the marks for this question. So we would have ended up with, it's VO minus, O minus over there, which picks up a H from, in this case, the solvent. I didn't associate marks with this, but if you drew it out, there's nothing wrong. It is correct. And the final product, which you needed to have written down, is that, of course, it's an alcohol. So you've got to know at least what the product is over there, that it's an alcohol. But the mechanism would have given, so 2 marks there and 1 mark for that. Then this over here is pretty much exactly the same thing, where we've got another mechanism. Now the nucleophile is not an H boron bond, it's now the carbon magnesium bond over there. So we are going to be, so we draw it out, and it's all the Grignard reagents work like the same sort of thing. It's this bond over here, adds there, and we get our intermediate alcohol, which is associated with the magnesium bromide, and there's our new bond that was formed. Last step over there, we're adding water, so the O minus is going to pick up that, and we get the hydroxide being formed over there. So the product is the alcohol. All right, this is very fundamental chemistry, also chemistry which you did last year in first year, so you should be able to do that. Okay, this question over here, so the question says that this was the attempt that what the student wanted to do. So researchers thought they'd form product A over there, but this did not happen. Instead, researched an unexpected cyclic compound. Show what happened. Well, the problem is that once we form this intermediate over here, magnesium bromide, okay, so we've mixed magnesium, that's formed over there. It's all very well to say, oh, now we want this to attack this electrophile over here, this ketone, to get this product. But the thing is, the molecule doesn't know that. It doesn't think for itself. It doesn't know what you wanted to do. Rather, it is looking over here. There is a functional group in the molecule which already is reactive. And so what's going to happen is that this bond is going to attack that one over there. And this is where you have to start counting things up. 1, 2, 3, 4, 5, 6. That's how many carbons there are there. This carbon is going to be connected to carbon number 2. That's going to make a 1, 2, 3, 4, 5-membered ring. So when we draw that out, we get a 5-membered ring. All right, and we just number this again. 2 is connected to 3, is connected to 4, is connected to 5, is connected to 6. 6 is connected to 2, that's the reaction that we showed. And on carbon 2 is also connected to carbon 1, and carbon 2 is also connected to the O minus, which is the result of the Grignard reaction. So once we add water to it, again, this is just the same as we had in the previous question. We can protonate that and we get the cyclic alcohol, and that would have given you all the marks. So you need to look out for things like that. We're on the home stretch now. This is saying, can you think backwards in terms of Grignard chemistry? How can we make this compound over here through Grignard chemistry? And the thing here is just to recognize that whatever carbon is connected to an oxygen, alcohol like this, that could have come, because Grignards give you alcohols as products, that could have come from a carbon-carbon bond formation. So either it's this carbon-carbon bond or it's this one over here. So either we cut here, this will be root 1 for argument's sake, or we cut here and it'll be root 2. So when we cut there, all right, the electrophile is going to be this, all right, and the nucleophile Grignard reagent is the aromatic magnesium bromide. Be careful when you draw these things out that you don't lose the number of carbons. Count them up. 1, 2, 3, 4, 5, and then aromatic ring. 1, 2, 3, 4, 5, and then the aromatic ring. If we cut over here, then the Grignard reagent, whoops, sorry, it's a mistake. The electrophile is now this, and the Grignard reagent is going to look like that other question we had just now with magnesium bromide. So it's isopropyl magnesium bromide. And that's that one over there. Count 1, 2, 3, 4, 5, and then the aromatic. So we've done that correctly. And then lastly, over here, this is why acid-base chemistry is so important. The alkyne over here, that H over there, is actually fairly acidic. And so with a very strong base, like methyl magnesium, because that's a C minus effectively, it's a very strong base. It's going to deprotonate that, and so it's important to draw that out as a minus over there. Actually, although we draw it out as a minus over there, that's not strictly correct because we've got this counter ion, the magnesium bromide, and then we know it actually forms a bond. So yeah, that's wrong. Rather, we want to draw it out like there, magnesium bromide, and the cyclopropane ring over there. And then when it reacts, this carbon over here, the sigma bond, right, from this carbon is going to attack over there. So it's a substitution reaction now, which you're going to see more of later. And so that's the product that we get over there. All right, that's the tutorial.